When working with data that unfolds over time, like spoken language, stock prices, or customer claim histories, traditional neural networks fall short. They treat each input as independent and have no sense of what came before. That's where recurrent neural networks, or RNNs, step in. Unlike standard models that process one chunk of data at a time and then move on, RNNs are designed to remember. They take in input step by step, word by word, moment by moment, while maintaining a hidden state that carries information from the past. This hidden state functions like a memory, helping the model build an understanding of the sequence as it progresses. Let's say you're using an RNN to read a customer's insurance claim, which might be a paragraph describing what happened. Instead of looking at the whole text at once, the RNN takes in the sentence one word at a time. At each step, it considers two things: the word it's currently reading, and the memory of what it's read so far. This allows it to gradually understand the context, much like how we make sense of a story as it unfolds. RNNs have proven particularly useful in applications involving sequences. In time series forecasting, they can track patterns in data to predict future values, such as estimating insurance risk based on historical trends. In speech recognition, they help transcribe spoken words in real time. In language modeling, RNNs learn how to predict the next word in a sentence or even generate coherent paragraphs. They also power chatbots and real-time translation tools, and they're increasingly used in summarizing lengthy claim reports in industries like insurance. Imagine an insurer using an RNN to automatically summarize a long narrative written by a customer. The model reads through the report, line by line, and outputs a short summary that highlights the most relevant facts. That summary can then be passed to a decision engine to approve or flag the claim. This speeds up response times and reduces manual work. However, RNNs are not without challenges. One key issue is the vanishing gradient problem, which makes it difficult for them to remember things that happened many steps earlier in a sequence. This means standard RNNs can struggle with long-term dependencies, like trying to understand the relevance of a sentence that was written 5 paragraphs ago. They also train more slowly and are harder to parallelize compared to other models like CNNs. To address these limitations, more advanced variants of RNNs have been developed. LSTMs, or long short-term memory networks, are designed to remember important information over long sequences by using gates that control what gets remembered or forgotten. GRUS, or gated recurrent units, offer a simpler version of this idea with fewer parameters but still good performance. There are also bidirectional RNNs, which process data both forward and backward, helping the model understand context from both directions. In summary, RNNs are the foundation of many powerful AI applications where context, memory, and sequence matter. They bring a sense of continuity to machine learning, something essential when dealing with data that tells a story over time. Whether it's understanding speech, reading a document, or forecasting trends, RNNs offer machines a way to think in sequence, not just in snapshots.